In this second video for Module 15, Weathering and Mass Wasting, we look at mass wasting. And remember that if we consider stages of denudation, or sort of the breakup and removal of material that are part of the external processes, the initial stage is weathering. So we've looked at that already, the breakup of rock, chemically or mechanically. In this second stage, this intermediate stage, we consider the downslope movement of material in response to gravity. Then there's a final stage as well, erosion and deposition. We'll look at that a little bit later. We can say that gravity is the energizing force behind mass wasting. So something to consider is the angle of repose, and that's the maximum angle at which material can remain at rest on a slope. And it's possible that if we increase the angle, material will no longer stay at rest. So at some critical angle, material begins to slide down or fall down a slope. And we can sort of test this idea if we use sand and pour sand in sort of just one place. Fine sand will build an angle of about 25 degrees. So this angle right here is about 25 degrees. More coarse sand will build an angle of about 35 degrees, and angular pebbles, just because they're irregular in shape, will form angles of about 40 degrees. So the angle of repose does change depending on the material. And here's the angle of repose just applied to a construction site. And you can see the angle is shown here in this red addition that I've added to the photo. So you can see the angle at which these rocks that are in the foreground will pile up in a construction site or a storage area. I should note that moisture will impact the angle of repose. So dry sand, for example, you can't pile it up at steep angles like you can wet sand. So wet sand, the water actually provides some tension, some adhesion between the particles and helps to hold them together. If sand becomes saturated, it's sort of the opposite thing happens, and the angle of repose becomes lower. Take the example of dry BBs. If you've ever had a BB gun, dry BBs are just little round, spherically shaped pieces of metal, and you can't really stack them very high. It's like stacking marbles. You can't stack them very high at all. Dry sand you can, and if we add a little bit of moisture, in this example, dry silica flour with irregularly shaped particles and a little bit of moisture, you can stack it even higher. Okay, let's move on and talk about some types of mass wasting. And we're going to go through a list here that's laid out in order of speed. So we can say the very fastest type of mass wasting are rock falls, where individual rocks are falling from the side of a steep place, a cliff, for example. And we know that rock falls present quite a danger and sort of long-term hazard to vehicle traffic in mountainous areas. So we can say rock falls involve rocks falling one by one. Here's a rock fall in Italy. You can see how far down this rock came from this way up on this slope and down all the way down the slope and right through this farmhouse. So pretty unfortunate situation. Where many rocks pile up over time, where there's, say, a weathering process, mechanical or chemical weathering, and pile up, we describe that feature as a talus slope. So talus would define just rocks that have piled up over time. And where those piles of talus begin to coalesce, sort of come together, we call it a talus apron. So you can see in this photo here, this is the talus apron here at the bottom of the slope, and you can see the chutes where rocks have broken off from this higher area and been directed down the chute to pile up to form these piles of talus and talus apron. Here's talus up close, and it really varies in size, and usually the pieces are pretty irregular in shape and size, so they can stack a little bit higher for that reason. So what are some methods that can be used to mitigate the danger of falling rock? Well, these are some examples from near where I grew up in Southern California. Laguna Canyon Road is a road that I've driven many times. Sort of connects the interior of Orange County with Laguna Beach, California. But these are places where they've had a real problem with rock falls. rock slides and individual rock falls. So they put in this chicken wire and these wire mesh fences to try to protect roadways. There's also been some experimentation done with catch fences to catch bigger rocks if those are falling in a particular area. And of course, in this example, this is a road that has a shed that's been built to try to protect it from rock falls. You can see this the shed sort of protects the road from a place where rock falls are pretty common. So second in terms of speed, a little slower in terms of speed, but often involving a lot of material, is the rock slide. So the rock slide is a little bit slower, but generally involves a lot more material coming down all at one time. So here's sort of the idea of a rock slide, everything sliding down in one mass. And we see some rock slides happen where there's a failure of the slope. So rock slides are somewhat dry, and again involve material not coming down one piece at a time, but coming down all at one time, and creating quite a hazard. Another example of a rock slide affecting, this is near Santa Monica, California, a home that's been affected by a rock slide. Again, dry. Rock slide in Andorra. This is a country that's right between France and Spain in the Pyrenees Mountains. Landslides happen along zones of weakness, such as bedding planes. So here we see some perhaps sedimentary rock that, or igneous rock that's been laid out in these parallel bedding planes that dip a little bit, and oftentimes the weaknesses in the bedding plane lead to rock slides happening as very abrupt movement of rock. And here's an example in a coastal area of some of these bedding planes, so you can sort of visualize what they look like. And of course, here is an example of a landslide. And notice that in the landslide, really everything comes down. The rock, the soil, the trees, everything. I mean, it's a really devastating. Here's one more view of this landslide that was captured in a video. To give you some idea of the causes of rock slides, I put together this table that gives you a feel for the triggers, such as the addition of moisture, which adds weight, and we'll talk about that a little bit later. On a looking naturally, that could happen from rainfall or snowfall, but humans can also contribute to that through water disposal, improper grading. Here's the addition of weight by adding volcanic ash or snow. A human contributing factor could be the placement of fill of building materials, vibrations, earthquakes, and thunder. On the human side, blasting and heavy equipment. This is a kind of a two-view or two-photograph view of a landslide that happened in California, the Cucina Landslide, and watch these neighborhoods right here. You can see that this area has already experienced some landslides, and here's sort of our after view right here. You see this part of the neighborhood just completely devastated, covered by material. Landslides also happen where entire slopes give away. So you could have part of a slope or an entire slope. This is a landslide scarp, the scar that's created by a landslide in a coastal area. Just everything came down. Another example of a scarp that's caused a real problem for this highway. And a slope failure in Oregon, where you can see this part of the slope here was even with this other part, and the whole thing just failed. I thought I'd mention landslides outside the U.S. One of the largest landslides, or in this case a rock slide, that has ever taken place was in Alberta, Canada, where 33 million cubic meters of rock were moved at Turtle Mountain in less than 2 minutes, killing about 70 people, as we say in the caption here. So pretty devastating rock slide. A landslide in South America that's wiped out this neighborhood. And this one is in Japan, where this roadway is completely covered. And in Taiwan, a highway covered by a landslide. So I think you get the idea. Just some examples of landslides around the world. NASA created this map so they could model lands that are most susceptible to landslides that come as a result of heavy rains. And you can see the more mountainous areas of the world, like here in South America along the Andes Mountains, and some parts of Europe, in the Pyrenees, and in the Alps, in the Himalayas, and elsewhere in Asia, and in North America here in the area of the Cascades, and some other mountain ranges in North America. We have some high susceptibility. Here's just some examples. Peru, a landslide there. Nepal suffers from frequent landslides, and Japan as well. I thought I'd mention, just when looking at some of the causes of landslides, I mentioned that I would touch on the effects of adding moisture, and this is sort of an example that comes from something that happened in my life when I was a little bit younger. An event. It didn't affect me personally, but I wanted to tell you the story. And this involves adding moisture to a slope. And going back for just a moment, an unsaturated hillside, moisture actually helps to hold pieces of rock and soil together. So here we see in this example unsaturated material on the side of a slope. You have some moisture in between particles that provides a little bit of adhesion, and the particles push against each other, and everything kind of holds things in place. But if you have too much moisture, these spaces in between the solid pieces, that can actually undermine the ability of that slope to stay together, and it can lead to and it can contribute to a landslide. And that's exactly what happened in Bluebird Canyon a couple of different times. And the time that I remember, I was a high school student in 1978 and went to help. I grew up just north of Laguna Beach and Newport Beach, but this is my example of the Bluebird Canyon landslide. And what happened in Bluebird Canyon? It's a pretty expensive area to live in. The homes are $1 million homes, and what the builders did is they sort of converted something that looked like the picture on the left here, natural chaparral vegetation, which is a characteristic Mediterranean vegetation of Southern California that's pretty dry, and they came in and they added a lot of landscaping. So they put in, trees and other types of expensive landscape to sort of increase the scenic value of their properties. The problem was that landscaping required a lot of water, a lot of additional water beyond what was needed for something that was a desert landscape. And so in 1978, they had these horrible landslides. Part of it was due to the fact that much of the soil was right on top of clay, and the clay was impermeable. So when you added all of this weight to the side of the hill, it was just this perfect surface on which the topsoil and the stuff on top would just sort of slide down because of the addition of that weight just across that clay. And this is a scene from 1978. This home is now kind of in this photo kind of a split level. This area right here was attached, and this landslide happened very abruptly. The problem with Bluebird Canyon is it wasn't the last time that Bluebird Canyon suffered landslides. There were additional landslides that happened in 2005, and even more recent than that. And you can see this is another view of the same area in 2005 that was hit yet again by a landslide, and another view of Bluebird Canyon in 2005. So how about some methods of mitigating landslides? Can you do anything? Well, you can. You can try to control things that happen on a slope. You can have ways of trying to reduce water. This is actually a culvert here that's been added to the side of this slope here. You see ice plant, which is a plant that does pretty well in helping to stabilize slopes. It's kind of a plant that you find in drier areas. This rock, the rock wall here is also has also been installed for that purpose, to sort of lessen the chance of a landslide. Some people will add plastic to the side of a hill if they know there's going to be rainy conditions. Another thing you can do is, if you have an area that doesn't have vegetation, vegetation's good at holding slopes together. You can seed those slopes. And this is hydroseeding, when they actually spray seeds onto the side of a hill before, and then subsequently water that area, or other types of plantings like this one. To try to increase the ability of the vegetation to hold that slope together. And here's what they did in Bluebird Canyon. They put in these pretty extensive and pretty expensive system of soldier beams, these beams that are running up and down, and then the grade beams running left to right. to try to mitigate some of the downslope movement of material. Here's another example, putting in additional barriers to try to hold slopes together. In the developing world, they might use, in some areas, bamboo, like this scene, to try to hold things in place, or prepare to even pour concrete if necessary. I wanted to mention one unique type of landslide is something that involves backward rotation. So if you look at this photo here on the right, you see that the movement of material is not really, it's not a long distance. It's just where the slope is given way, and it sort of sags here and actually tips back in a process that we call backward rotation. In the next slide, I'll show you a pretty good example of backward rotation. Here you can see it. If you look at the trees here, sort of in the upper center of the photo where I'm circling right here, those trees were up here at the top before the landslide took place. So what happens is you have this downslope movement that we call a slump, which is not a real long distance, and then the slope sort of tipping back a little bit. We call that the backward rotation. Just to give you an idea of landslide potential in different places in the U.S., again, it's pretty closely tied to more mountainous areas. In Oklahoma, we see areas that are not in the area in and around Tulsa, and then the southeastern part of the state having the highest landslide potential. So again, places where you have steeper slopes. Some landslides, in terms of human impacts, have been pretty devastating. And we see the number of fatalities here in a few landslides triggered, in most cases, by earthquakes. We see one in the USSR, which is now Russia, from 1949, that killed 12,000 to 20,000 people, an estimated number. In China, there was an earthquake-triggered landslide that killed 200,000 people. So, sort of a staggering number of people. All right, working back through our list, I promised that I would sort of go in order of speed. And slower than a landslide is a flow, is a earth flow. And this earth flow in Australia is just a slow sagging of material in response to gravity. Some other examples of a flow here, it's kind of hard to see in this photo here, but this slope is very slowly moving down towards the roadway, and it may eventually cover parts of the roadway. Here you see another example of an earth flow. Sometimes moisture is involved. Most often moisture is involved in earth flows because it adds weight. And again, gravity is really the energizing force with an earth flow. Another earth flow, again, not a rapid movement, but pretty devastating. You can see this house has just pretty much been devastated by an earth flow behind it. The house didn't move, but the earth flow came in behind it and really badly damaged the house. One of the faster types of flows is a mud flow. So mud flows are sort of a little bit of an exception here to the speed. They happen pretty rapidly and often after heavy rains, and often associated with a fire. So you might have a fire that might affect an area, burn down trees, disrupt ground vegetation, and then when you do have heavy rains, a mud flow can be the result, and they can be pretty devastating. Here's a mud flow in California that sort of swallowed up this SUV, and I put this video in here so you can see what a mud flow might look like if it was chasing you. This was the drone footage of a mud flow, and you don't want to be caught in one of these things. I mean, they're like a flash flood. I mean, they can be pretty hazardous. And some aftermath of a mud flow in Utah, so you can again appreciate the size of areas that are affected. Here's that same neighborhood in looking at a mud flow that's sort of done a lot of damage in a subdivision and a shopping center that's been affected by a mud flow. And this mud flow in California has sort of coarser rock were carried by this mud flow. And again, another view. Many of these triggered, as I mentioned, by fires and subsequent downslope movement of material when there has been heavy rains. Can you do anything to mitigate mud flows? Well, you can put in mudslide barriers like this one. You have to kind of know where the mud flow is going to be coming in order to be able to plan this sort of thing. And I'm not sure how effective it is over time, but these are being tested. One type of mud flow I wanted to mention is associated with the eruption of a volcano, and there's a pretty bad mud flow that followed the eruption of Mount St. Helens in 1980. This is had a subsequent small eruption of Mount St. Helens in 1982. But lahar is a slurry, as I say on the slide, a slurry of pyroclastic material. This stuff that was essentially ejected from the volcano, and then it mixes with water and flows down slope, and it can be pretty disruptive. This is a lahar from Mount Pinatubo in the Philippines. All of this material was carried by running water, and when there's heavy rains, these mud flows can be pretty significant. So I asked the question, what would happen if Washington State's Mount Rainier were to erupt? We had pyroclastic material that was picked up by heavy rains and carried down slope. Well, you could have some effect of the lahar even as far as a place like Tacoma, Washington. This is Tacoma here, all the way on the Puget Sound, and you see these pathways right here. These different colors represent valleys that it's estimated where scientists believe that the lahar muds would be carried by heavy rain, and probably some melting of glaciers on Mount Rainier. The slowest type of mass wasting, we get down to rock glaciers, represent very, very slow movement of talus. This is all that talus that I was talking about a little bit earlier. What's interesting about the rock glacier, imagine these rocks here at the toe of this rock glacier are moving because they're being pushed by rocks farther upslope. So you have new rocks that are being added to this thing, and it's like sort of like a conveyor belt, but the rocks up above are creating pressure to push the rocks down lower on the slope, and that's what drives the movement of the rock glacier. So they're not a glacier in the sense of glaciers like snow and ice, but they do operate in something of a similar way, where you have pressures from higher elevations on material that's lower that causes it to move. Here's another example of a rock glacier. These lobes, these folds here, and this is all talus right here. So imagine that's not really snow and ice so much. That's just talus. That's just those chunks of rock that are piling up here at the base of the slope and are being pushed over time. So this whole thing is being pushed by the weight of additional and pressure from additional rock that's being added. The very slowest type of mass wasting is in the category of creep, and it's an imperceptibly slow movement of slopes. And here you see the whole side of this hill right here is being affected by creep. You can see these trees that are sort of bending as they try to adjust. These are aspen trees as they try to adjust to the slope as it continues to sag. A few examples of creep that we can see in things like this is below a bridge. These are paving tiles that have been added below a bridge, and they're kind of messed up by some creep that's going on. This fence posts pushed over, this rock it's been bent. These layers of strata that have been bent by the slow process of creep happening up near the surface. Another example of creep shown in this photo with this guy, where you can see the direction of movement here from left to right. And if you go into an area, I've seen these in a few places in Alaska. We call this the Drunken Forest, where soil creep has caused these trees to sort of, be facing different directions. So a crazy thing, and creep caused the split in this tree. So you see a very slow, imagine very slow downslope movement has split this tree, and also caused the damage to this retaining wall, rock retaining wall. One type of creep that I wanted to mention happens in high elevation areas where layers of rock and soil begin to thaw as you go into the spring months, and when they thaw, they begin to sag down the mountain. So you may have a layer of rock that's below that doesn't thaw, that remains frozen, permanently frozen ground. And so we call this solifluction, this freezing and thawing that happens in this relatively thin layer of rock and soil that's above the permafrost, above the permanently frozen ground, and it sags down slope in response to gravity, producing these solifluction lobes. And here's sort of an animation that kind of shows you how that happens. that I've created. So you can see here's the thawing out in this example right here, and then the sagging down slope of the whole thing in response to gravity. As you go into winter, freezing again, and then thaws out, and the process continues over time. And this is a soil flexion lobe here shown in the upper photograph.